Hello and welcome to this video. So what we want to do in this video is to deal with the second case. So that's case 2, where we have real repeated roots. So we still have real roots, but in this case they're repeated. I'll do this by means of an example. Let's say we're told to find the inverse Laplace transform of a system that is defined as, say, 2 over, okay, let's not use 2, I've used 2 a lot, 4 over s plus 1 squared. Okay, or let's even make it a little less obvious. Let's say s squared plus 4s plus 4. Now, if you look at the denominator, you know I have just simply made that s plus 2 squared. That's intentional. So we're finding the inverse Laplace transform of this. That's the same thing as saying we're finding the inverse Laplace transform of 4 over s plus 2 into s plus 2. Now that is s plus 2 squared. When you have repeated roots, the way we deal with it, so we have 4 over s plus 2 squared. We don't say k1 over s plus 2 and k2 over s plus 2. No, instead we have k1 over s plus 2, and then we have k2 over s plus 2 squared. Okay, so we have one case to deal with, one term to deal with the case where you don't have the square, and the second term to deal with the case where you have where you have the square in your denominator. So let's go ahead and try to solve this. If I expand this term, that's using the first method that we used for the last class, if I expand this term, what I have is k1 into s plus 2 plus k2 all over s plus 2 squared. In other words, the numerator is k1s plus 2k1 plus k2 over s plus 2 all squared. Now this, the numerator, you can, so if we equate the numerators, we have that k1s will be equal to 0. Reason for that is, why is k1s equal to 0? There's no s term on the left hand side. So k1s is simply equal to 0. That simply implies that k1 is equal to 0. Now k2, that leaves k2, and k2 is simply equal to 4. So what we have arrived at is that this is equal to, this expression is simply equal to 4 over s plus 2 all squared. So it's like we've gone a full circle with the right hand side is back to what we had originally. But that is not weird. That isn't strange actually, because instead of going through all of this that we did just now, what we should have done is go ahead to find the inverse Laplace transform of 4 over s plus 2 all squared. Now, can we find the Laplace transform of this directly? The answer actually is yes. There's no point in going to partial fractions. First of all, partial fractions just bring us back to this same point. Okay, partial fractions bring us back to this same point. But can we find the solution to this directly? Okay, let's think about what this looks like. This looks like something over something squared. Now, this is like, if you want, s plus a squared. So this kind of is reminiscent of the Laplace transform of a constant multiplied by e to the power of minus at times tu of t. If we found the Laplace transform of this, what do we get? We have k multiplied by, now tu of t is 1 over s squared. But because you have e to the power minus a, what you have is s plus a squared. So k over s plus a squared is exactly what we have here. So the inverse Laplace transform of this simply ends up becoming k, which is 4, times e to the power of minus a is 2, minus 2t, multiplied by t u of t. So we did not need partial fraction expansion for that because of this particular because of the particular question that we're given. So what I'll do is to take another example. So if you want, that example was actually a trick example because really we didn't need partial fraction expansion for it. However, we did see the procedure we would have gone through if we had needed partial fraction expansion. So let's go ahead and pick a different example, but this time we will need partial fraction expansion for it. So we are told to find the inverse Laplace transform of, let's actually pick something that is now similar to what we are actually, to, if you want, the problem that we've been trying to solve that we just haven't solved yet. So let's say we have 4 over s squared plus s plus 1. We want to find the inverse Laplace transform of this. To do that, we'll first of all decompose this term, this expression, 4 over s squared into s plus 1. We decompose that into partial fractions. That'll be k1 over s. Now, s plus 0 is repeated. So in other words, s is equal to 0. The root s is equal to 0 is repeated. That means we'll have two terms that talk about it, k1 over s and k2 over s squared. And then we have a third term representing the third root over s plus 1. Okay, so we have k over s1, k2 over s squared, plus k3 over s plus 1. Now we have an expression. Now we can work with this. Okay, so let's start out. Let's use method 2 in this case. Instead of using method, we could use method 1. Okay, so maybe let's go ahead and use method 1. That I noticed seems to be initially what is most comfortable, what students are most comfortable with when starting out. So if we're going to expand, or if we're going to combine all this together into a single fraction, you end up with k1s plus, no, k1s, k1s into s plus 1. So maybe I should write the denominator so that it's clear. S squared into s plus 1. Okay, so you have k1s into s plus 1 plus k2 into s plus 1 plus k3s squared. Okay, so that is now our expression. Now you have three terms and three unknowns, that is. So to equate your numerators, you have the coefficients of s squared. Okay, yeah, so coefficient of s squared, you have k3 is the coefficient of s squared is equal to 0 because there's no s squared in the numerator over on the left hand side. So k3 is equal to 0. Now coefficients of s, sorry, I'm wrong about this. K3 is, let me rewrite this numerator once again so that, or let's just write the expression, equate the numerators. 4 is equal to, there's another s squared term here which I did not factor in just now, k1s squared plus k1s plus k2s plus k2 plus k3s squared. Okay, so this is now our term. Now we can work. So we have k1 plus k3 is equal to 0. That's our equation, equating the s squared terms. And then we have, equating the s terms, you have k1 plus k2 is equal to, also being equal to 0. And then now taking the standalone terms, you have your k2 is equal to 4. Okay, so k2 is equal to 4. If you put in 4 in here, or if you want, this first term tells me that your k1 is equal to the negative of k3. This second expression, second equation tells us that my k2 is equal to the negative of k1. Third term tells me that k4 is equal to 4, and that implies that my k1 is equal to minus 4, and that implies that my k3 is equal to 4. Just confirm that k2 is 4, k1 is the negative of that, so that's minus 4. K3 is the negative of k1, so that's equal to 4. Good, so we have our three terms. So now what we want to do is to find the inverse Laplace transform So our task is now to find the inverse Laplace transform of minus 4 over s plus 4 over s squared. K3 is also 4 plus 4 over s plus 1. Just to make sure we've written that correctly, let's just go back and check that once again. So that was k1 over s, okay? So k1 over s plus k2 over s squared plus k3 over s plus 1. K1 is minus 4, k2 is 4, and k3 is also equal to 4. So this is what we have. Now, to find the inverse Laplace transform of this, I believe I can just write this out and you already know the solution to this. So minus 4 u of t plus 4t u of t plus 4 exponential negative t. And this is our solution. This is the inverse Laplace transform of that original expression. So when you have real and repeated roots, remember the root that is repeated, you're going to use that twice. Your numerator will be k1 in one case and k2 in the other. You have two different constants in your numerators, so whether k1, k2, k3, k4, whatever parameter you use. You have two different constants. So one constant over the root itself, a second one over the square of the root. Note that if this had been s plus 2 squared, like we did in this example, even though it was not necessary for us to use partial fraction here, we had s plus 2 and then s plus 2 squared in our denominators. So that's how you deal with systems when your b is equal to when you have repeated roots, okay? When you have repeated roots. Now, one thing I did not do is to test to show that the roots were repeated. So if you don't mind, let me just show that here using this first example, this case 1 example. The case 2 example is obvious, but using this case 1 example, let's say we're told to find b, we wanted to find b squared and 4ac. B is 4, so b squared is equal to 4 squared, which is simply equal to 16. Now, 4ac is equal to 4 multiplied by a is 1 multiplied by c, that is 4. And that is also 4 by 4, which is 16. So your b squared was equal to 4ac, and that tells us straight up that we have a repeated root. So that will be it for this video, and in the next video, we'll deal with complex or imaginary roots. Thank you.